This lesson is the last lesson we need in order to be able to graph functions without a calculator, in order to put together everything with calculus and with pre-calculus in order to graph or sketch a function without using a graphing calculator or a graphing utility or anything like that. This lesson is going to combine and add to everything we know about asymptotes. There are three types of asymptotes. Excuse me. There are vertical asymptotes, which we talked about when we talked about limits. There are horizontal asymptotes, which you would have talked about in your pre-calculus coursework, but we're going to focus on again today a little bit. And then there's slant asymptotes, which we'll touch on at the end of this section. Vertical asymptotes, we're going to relate this all to limits. And with vertical asymptotes, it happens the limit as x approaches a number and the function goes to infinity. So with a vertical asymptote, x is getting really, really close to a number. As x approaches a value, it's either going to be going up to positive infinity or down to negative infinity. Either way, up to positive infinity, down to negative infinity. So vertical asymptotes occur as the limit as x approaches a number. Horizontal asymptotes are kind of backwards. Horizontal asymptotes happen at the end. Limit as x approaches positive or negative infinity, and then the value of the function will be approaching a number, so kind of the opposite of vertical asymptotes. You would have talked about horizontal asymptotes in your pre-calculus coursework. You might have referred to it as end of behavior. What happens to the function at the end? Either as x is really big, as x goes to positive infinity, or as x goes to negative infinity, as you get really, really small. What happens in the middle of the graph doesn't matter. It's what happens at the end that matter when we talk about horizontal asymptotes. What does the function want to be as x gets really, really big or as x gets really, really small? With vertical asymptotes, you would write the equation of the asymptote as x equals that number. Well, with horizontal asymptotes, we're also going to write the equation of the asymptote as y equals the number. Slant asymptotes also happen at the end, and the function will still, it's a limit as x approaches infinity, far to the right or far to the left, and it'll still go to positive or negative infinity, but the slant asymptote will approach a line, which we'll show you an example of that a little bit later. Horizontal asymptotes almost always occur when you have rational functions, numerator over denominator. Just like vertical asymptotes happen when the denominator is equal to 0, horizontal asymptotes occur mainly with rational functions as well. We got a function here, 6x squared over 2x squared plus 1. In order to find a horizontal asymptote, we want to find the limit as x approaches infinity. As x gets really, really big, as we go to the ends, what's happening? We're going to take a tabular approach, meaning we're going to use a table to plug in some numbers into this function and see what happens on each side, just to get some idea with the actual values of the function. So starting at 0, right in the middle of the graph, the function's at 0. 0 over 1 is 0. Then if you plug in 1 or negative 1, the function's at 2. Then as you start getting bigger, 10 and 100 each way, at x equals 10, the function goes to 2.985. At x equals 100, 2.99985. So you can see, and the same to the left, 2.985, 2.99985, because these are squares doing the same thing, the positive and the negative. You can see that as the numbers get big, the value seems to be approaching 3. Y wants to be 3. Instead of it happening as we get towards a number, as we did with limits in the first section or chapter, it's happening as we get away, as we go to the ends. So that's the difference between vertical asymptotes as x approaches the number and horizontal asymptotes as x goes to the end. So you get big or small. So the limit as x approaches infinity of this function is 3. As x gets really, really big or really, really small, the value is going at 3. So there's a tabular approach, but there's also algebraic methods to find these limits or to find the horizontal asymptotes. Something that's important to remember, one limit important to remember, we talked about it back in probably your pre-calculus work. We touched on it a little bit in the limit section. But the limit as x approaches either plus or minus infinity, positive infinity or negative infinity. It gets really, really big or really, really small in the negative value of some number. It doesn't matter what the number is, over an x term in the bottom, x to a power. If it's some number in the numerator, over x in the bottom, over an x term in the bottom. As x gets really, really big, that numerator, that top, stays the same. It stays the constant. The denominator gets really, really big. So a number over a really, really big number And as that number keeps getting, that bottom number keeps getting bigger and bigger, that fraction pretty much becomes 0. That fraction goes to 0. So the limit, as x approaches either positive or negative infinity, of a number over a power of x equals 0. That limit goes to 0. So, just like limits in chapter 1, you take the limit as x approaches infinity of 6x squared over 2x squared plus 1, the same function. We're going to try direct substitution. Try that first, see if it's easy. Plug in infinity. Well, the top goes to infinity, the bottom goes to infinity. 6x squared, as x gets really, really big, gets really, really big. 2x squared plus 1, as x gets really, really big, the bottom gets really, really big. So we get infinity over infinity, which is once again called, or another form, that's an indeterminate form. We can't determine the limit in this form. 0 over 0 was our common indeterminate form when we were talking about limits in chapter 1. Now we're going to see infinity over infinity as our indeterminate form in this section. So the algebraic trick, in the first section when we talked about 0 over 0, we would factor or divide out or multiply it all by a form of the number 1, something over itself. Well, here, the trick is going to be, we're going to divide every term, every single term, by the highest power of x in the denominator. So you look in the denominator of the fraction, and you find the highest power of x. In this case, it's x squared. And you divide every term on the top and the bottom by that power, by x to that power. No coefficient, just x to that power. So we take 6x squared, divide by x squared. 2x squared, divide by x squared. 1, divide by x squared. And you see that here. The limit as x approaches infinity, 6x squared over x squared, 2x squared over x squared, plus 1 over x squared. Then you simplify algebraically, just like back in chapter 1. Simplify, then reevaluate at that value. So 6x squared over x squared goes to 6, 2x squared over x squared goes to 2, 1 over x squared stays. Now we reapply the limit. We do direct substitution again. Limit as x goes to infinity of this equivalent form. Well, as x goes to infinity, 6 stays the same. Nothing happens to the 6. Nothing happens to the 2. As x goes to infinity, 1 over x squared, same as up here. A number over a power of x. 1 over x squared, x gets infinitely big, this goes to 0. So this becomes 6 over 2 plus 0. 6 over 2 is 3. So we get the same exact limit we got with our tabular data. With this table of values, you still get 3, but now you found an algebraic way to do that, so you don't have to plug in a bunch of numbers. And here's a picture of the graph right here. You see in the middle, the function is doing whatever it does. It's not going towards anything. But at the end, as x is really, really big, you see the function's going towards a horizontal line here. And that is value y equals 3. Same as x gets really, really small. You're looking for end behavior at the ends. All right, another problem. Just like in the last problem, the power, the degree of the numerator is going to be the same exact degree as the denominator. For the last one, they were square on the top and bottom. This one, we both have a power of 4 on the top and bottom. So you get limit as x goes to infinity, 12x to the 4th plus 6x squared minus 1 over 3x to the 4th minus 4x squared plus 7. Plug in infinity, you get infinity over infinity. They both go up infinitely. So you have another indeterminate form. So you go back through. This time we're going to divide everything by an x to the 4th. Highest power in the denominator. Divide each term by an x to the 4th. Simplify it. X to the 4th cancel, you're left with a 12. 2 x's cancel, so you're left with a 6 over x squared. 1 over x to the 4th stays. Bottom, x to the 4th cancel, you're left with 3. 2 cancel, so you're left with minus 4 over x squared. 7 over x to the 4th stays. Now that we've simplified this and have an equivalent form, now you want to resubstitute. Plug infinity back in. Limit as x goes to infinity. Well, the 12, nothing happens to. These two terms with an x term on the bottom go to 0. So this becomes 12 plus 0 minus 0. So our numerator is 12. Our denominator is 3 minus 0 plus 0. 12 over 3 simplifies to 4. So our limit here is 4. So the first two problems we looked at had the numerator and the denominator with the exact same degree. Now we're going to look at a problem where the numerator has a greater degree and one where the numerator has a lower degree. In this case, the denominator has a higher degree. We have the limit as x goes to infinity, 3x minus 1 over 2x cubed minus 4. So your higher degree, your higher power is in the denominator. Plug in infinity, the top still goes infinitely high, the bottom still goes infinitely high, so you get your indeterminate form again. Divide all terms by the highest power of x in the denominator. Denominator is here, highest power is x cubed. So every term gets divided by an x cubed. 3x over x cubed minus 1 over x cubed, 2x cubed over x cubed minus 4 over x cubed. Well, one of these x's will change, or cancel, I should say. So you get 3 over x squared minus 1 over x cubed, that stays. The x cubes cancel here, so you're left with 2 minus 4 over x cubed. Now you have an equivalent form. Now insert your limit, insert your value you're approaching. As x goes to infinity, 3 over x squared goes to 0, 1 over x cubed goes to 0, so your numerator is going to be 0. Your denominator, the 2 stays, 4 over x cubed goes to 0, so you're left with 0 over 2. So 0 over 2 is a number, and you get 0. So this function here, if you graphed it as x goes to infinity, positive or negative, it would be approaching the x-axis, approaching the line y equals 0. It's coming closer and closer to the x-axis. This was a problem where the denominator had a higher power than the numerator. Now we have the numerator with a higher power than the denominator. We've got an x to the 4th on the top in the numerator, an x squared in the denominator. We're still taking the limit as x goes to infinity. Plug it in, they both go to infinity, so we have our indeterminate form. Divide by, this time remember, divide by the highest power in the denominator, so we have an x squared. Even though there's a 4th in the top, we're still looking at the denominator. Over x squared here makes us 6x squared. The x squared cancels here, so we're left with minus 3, 7 over x squared. X squared over x squared is 1 plus 4 over x squared. So now we've simplified this, put it in the equivalent form. Now let x go to infinity. 6x squared as x goes to infinity goes up as high as it can, infinity. Minus 3 stays, plus 0, so the numerator is going to go to infinity. The denominator is going to go to 1 plus 0, so over 1. So this graph is going to get infinitely big as you go to the right, as x goes to infinity. So to sum this up, 3 types of problems for limits as x goes to infinity. You have where the numerator and denominator have the same degree. You have where the numerator has a lower degree than the denominator. And you have where the numerator has a higher degree than the denominator. First type, if the numerator and denominator have the same degree, then the limit as x approaches infinity will be the ratio of the leading coefficients. We'll go back a couple. 6x squared over 2x squared plus 1. All right, same degree in each. The limit as x goes to infinity is going to be the ratio of the leading coefficients, the coefficients of the highest power. So the 6 and the 2. 6 over 2 is 3, and going through that process, we did get the limit was 3. That's approaching 3. The next one, the leading coefficients, because we had powers of 4 on both. 12 and 3, 12 over 3 is 4. So your limit's 4. This is a shortcut you can take. Same power, the same highest power in the numerator and denominator. Take those leading coefficients and divide them out, and that will be your limit as x approaches infinity. If the denominator has a degree greater than the numerator, so you have a higher power on the bottom than you do on the top, then the limit as x approaches infinity will be 0. So if the denominator is higher, you're going to be left with zeros in the top. Something will cancel in the bottom. You'll be left with a number in the bottom. So you'll be left with 0 over a number. The denominator has a higher power. That's always going to go to 0. If the numerator has a degree greater than the denominator, now the numerator has a higher power, then the limit as x approaches infinity will be plus or minus infinity. Some books will tell you that the limit does not exist. I would prefer you write it as positive infinity or negative infinity, depending on which way, if it's going up or it's going down. And here's that example. You had a power higher in the numerator, 6x to the 4th over x squared. So the higher power is in the numerator. The variable stays. So the numerator goes to infinity, the bottom goes to the denominator goes to a number, and you're left with infinity over a number, which is infinity. So using these rules, You can solve limits as x goes to infinity problems without having to go through that whole process. Now we're going to do a problem where you have a radical in your rational function. Limits as x goes to infinity or negative infinity when you have a radical in your rational function. This is going to be a little bit different than the other ones. You're going to, in fact, have two horizontal asymptotes in these types of problems. First, we'll go over how to solve this algebraically. Then we'll go over why you have two. You have limit as x goes to infinity of 5x plus 2 over square root of 3x squared plus 4. So you send direct substitution, you send infinity in there, you get infinity, square root of infinity, still infinity. So you get infinity over infinity, you get your indeterminate form. So now you're going to divide through by the highest power of x in the denominator. But in your denominator, under the radical, you have an x squared. So you divide under the radical 3x squared over x squared and 4 over x squared. But in your numerator, since in your denominator you're dividing by the square root of x squared, in your numerator you're only going to divide by x. 5x over x and 2 over x. Since the square root of x squared is x. If it was an x fourth in under the radical, then you would divide the denominator or the numerator by an x squared. You take the square root of whatever that highest power was. Simplify this, you get 5 plus 0 as x goes to infinity, and you get 3 plus 0 on the bottom. So you get the limit as x goes to infinity of 5 over radical 3. Now, as you know, when you take the square root of a number, it has two values, a positive value and a negative value. Square root of 25 is 5 or negative 5. Well, as x goes to infinity, as x gets infinitely big on the x-axis going to positive numbers, your square root is going to be a positive value. But as x goes to negative infinity, as x gets infinitely small, you're plugging in negative numbers. Now you're going to have to take the negative radical, the negative square root. So you do the same thing, but when x goes to negative infinity, you still divide through by the highest power. It's still that trick where it's x squared under the radical, but an x outside on the top. But that square root now becomes a negative radical 3. So the limit as x goes to negative infinity, as you're plugging in negative values, is going to be negative radical 3. So this is going to go over 5, or the limit's going to be 5 over negative radical 3, or negative 5 over square root of 3. Now the little picture here where you see this actual function, and you see, as you move to the right, as the function moves to the right, it is approaching a positive value, it has a horizontal asymptote right here. As it moves to the left, it's approaching the negative value, so you have two horizontal asymptotes. If the sign in the numerator was a negative sign, this would be switched, because you would have a negative over a positive as you went to the right, so it would be going down, and a negative over negative as you went to the left, would be going up. The only thing that's negative when you do this is the square root sign, not the whole thing. The square root sign's negative, the radical sign's negative, and if the numerator is also negative, they'd still cancel each other out like normal math. Last thing I want to talk about in this section is what's called slant asymptotes. Now, as you're finding limits as x goes to infinity, no matter what, those rules apply. If the numerator has power higher than the denominator, the function is going to go to infinity or negative infinity. But remember, our goal in these first 5 sections was to put a bunch of stuff together so that we could graph, or we could sketch functions, sketch curves. Well, one thing that may happen is you may have a slant asymptote that fits in nicely in this section. If the degree of the numerator is exactly 1 degree higher than the denominator, so in his case I have an x squared and x minus 2, then you are going to have a slant asymptote. It's going to be a diagonal line that the function approaches from both sides as you go left and right. We'll see a diagram of that. Actually, you can see it right here. We can even look at it before we see what it is. You see the graph of this function here, and you see it's going up infinitely to the right, down infinitely to the left. But if you look carefully, you can see that there's a line here, that this line, or this curve is approaching here, and this curve is approaching here. They're approaching this slanted line as they go to the right and to the left, the positive infinity and negative infinity. You also see a vertical asymptote at x equals 2 because the denominator equals 0 at x equals 2. So you have two types of asymptotes here. But in order to find the equation of a slant asymptote, which is very helpful when you're curve sketching, when you're making a picture of the graph without a calculator, you're going to use long division. So a fraction is just a division problem, top divided by bottom. So you're going to go back to, when you learned how to divide back in 3rd grade or so, you make your division sign, the top here, the bottom here, you got to figure out what to do. I want x to turn into 2x squared. So I need to multiply this whole thing by 2x. X times 2x is 2x squared. 2x times -2 is -4x. Now I'm going to take this and I'm going to subtract it from what I started with. 2x squares cancel. -3x minus -4x is x. Bring down my next term, plus 1. Now I want x to turn into an x. Well, x times 1, positive 1. So it's going to be an x minus 2. Subtract the whole thing. X minus x cancels. 1 minus -2 is a 3. And that's going to be, I'm going to have a remainder of 3 out of x minus 2. So it's plus 3 over x minus 2. You should remember this from your pre-calculus work, right? Maybe even your Algebra 2 course. The equation of my slant asymptote, the equation of the line that this curve is approaching, is y equals 2x plus 1. So there's the equation of your slant asymptote. This remainder on the end accounts for the little bit of space between this curve and the actual line. As x gets infinitely big, this is going to go to pretty much 0, but there still will theoretically be a very little bit of space between the curve and the line, so that's why you have that little bit of remainder. But this is saying that this curve approaches this line, y equals 2x minus 1. So you have y-intercept of -1 and a slope of 2. You can see that looks pretty good for that curve right there. And the last thing we're going to talk about, limits at infinity with the trig functions. We're going to use what's called the squeeze theorem to find the limit as x approaches infinity of a couple functions involving trigonometric ratios or trigonometric curves or values. So the limit as x goes to infinity of sine of x over x. Well, if you plug in x as x goes to infinity, sine of x doesn't go to anything. It oscillates up and down. The regular sine curve, as x gets bigger, it doesn't change. It just keeps repeating, repeating, repeating. The bottom goes to infinity. So you get something oscillating to infinity. But if you think about that sine curve, if you think about y equals sine of x, the biggest it ever gets is positive 1. The lowest it ever gets is negative 1. It oscillates between 1 and negative 1 and all the values in between. So we can use that idea to say that the sine of x over x will always be bigger than or equal to, greater than or equal to, negative 1 over x. It will never be less than negative 1 over x because sine of x can never be less than negative 1. And it will never be more than 1 over x because sine of x never gets bigger than 1. So sine of x over x will always be between the graph of negative 1 over x and positive 1 over x. So it's always between them. Now, if you take the limit as x approaches infinity of negative 1 over x, well, number over a variable as it goes to infinity, that's going to go to 0. It's going to go to 0 from the bottom. If you take the limit as x approaches infinity of 1 over x, well, again, number over a variable as x gets really, really big, that's going to go to 0. So this is going to be positive values getting close to 0. This is going to be negative values getting close to 0. So these two functions are going to start big, and they're both going to attack the x-axis. They're both going to approach the x-axis. Well, because sine of x over x is always in between these, we use what's called the squeeze theorem, meaning it's always squeezed between these. If we know these two numbers are approaching infinity, or approaching 0 as x approaches infinity, then we know that it's going to take this curve and kind of keep it squoze, or it's going to squeeze it between them. So if these two functions approach 0 as x approaches infinity, then the limit as x approaches infinity of sine of x over x must also be 0, since it must always be between these two values. I would encourage you to graph this function and look at it as x approaches infinity, and you'll see that the curve starts off as a regular sine curve, or similar to the regular sine curve, and then the humps and the valleys get closer and closer together. You'll see it kind of oscillates up and down, but very tight to the x-axis.